So it turns out that all of special relativity can be derived from two basic principles. The principle that physics is always the same in all inertial reference frames, and the second is that light travels at the same speed in all inertial reference frames. And because the fact that light travels at the same speed in all inertial reference frames is a very odd way for velocities to add up, we had to actually change how inertial reference frames were related. And so we came up with the Lorentz transforms, which tells us how we do boosts, how we go from one frame going at one speed to another reference frame going at a different speed. And we've been slowly working towards turning all this machinery into a proper four-vector machinery. So we've got our covectors, we've got our vectors, we have the metric that turns covectors into vectors, and we started discussing the fact that you can turn position vectors, and position vectors are now space-time events rather than just space positions. So we discussed that we could turn positions into three categories. We could have distances that were space-like. In other words, there's a frame in which they are exactly space and not time separated at all. We have those that are separated on the light cone, and then on the light cone means that a light signal can travel from one event to the other, traveling at the speed of light. And then we have time-like, and time-like ones, two events separated in a time-like way. There's some frame in which they are separated only by time. In other words, they're at exactly the same place at different times. Now, if you have two events separated in a time-like way, then if you integrate up the interval between them, then you end up with the proper time. That's the time that the clock is going to recognize there. We know that because there is a frame where it is exactly the proper time. You're sitting there and you've got your clock. The fact that it's true in all frames, if you integrate up something that's a scalar, something that's the same in all frames, then you're always going to get the same answer in all frames. So whatever frame we calculate this, we're always going to get the proper time for that clock. And then the last thing we did was we discussed the idea that momentum is actually a four-vector. If it's going to be in special relativity, it has to be in some kind of four-vector form. And so we have the momentum vector, and we also found that we had the energy attached to it. So it's actually the energy momentum four-vector. And we've written that in various different ways. So you can, for a massive particle, you can talk about the mass times the velocity. For a massless particle, in fact, this version of it still holds. Let's just do an example now. We'll do it in two stages. The first is I'll set it up, and the second is you can see how I solve it. But try and solve it by yourself first. So let's assume that we have some kind of photon coming in. This photon will have some momentum. That lambda will be for the photon. And we have some particle. Maybe it's a nucleus, maybe it's something else. All I know about it is that it's at rest and it has some mass m. And then after these things collide, we're just going to have the particle. So the photon is going to be completely absorbed, and in fact this mass may have changed, and it may have some kind of velocity or momentum. Okay, and I want you to work out exactly the properties of this mass and that velocity and so forth on your own.